So in the previous video we talked about Gaussian linear regression, and we said that the of uh, uh, likelihood of y given x and w would be normally distributed with mean w transpose x and variance sigma square, and then we use the maximum likelihood approach to estimate the value of w. And then once we had that w from by maximizing the likelihood of the given data, then we use that w to predict the value of the y for a new x. Now, one thing that method is prone to is overfitting the data, because we are just maximizing the likelihood of the given data, and we might overfit that. We might find a WMLE that really fits that given data very well, but does not do well outside that data. So one way to deal with this problem is by introducing a prior on the W. So we say that we had this, right? Yi is normally distributed with W transpose Xi and some sigma square, which can also be written as 1 by A, where A is the precision of this univariate normal. Okay, so this was the the model that we assumed for the likelihood of y given W and X. And then furthermore, we can say that this W, we can put a prior on this, and we can say that W is a multivariate normal with mean vector 0 and covariance matrix 1 by B times the identity matrix, where B again is a precision along each dimension of this multivariate Gaussian, right? And when we say this, then the posterior of W given the data becomes the product of the likelihood and the prior. Okay, we don't have to say this for this to be true. This is always true, but we have assumed a certain form for the prior now. And the likelihood is a normal distribution. The prior is a normal distribution. These two are conjugate priors for one another. So when we multiply them, we have a quadratic form here in the likelihood and a quadratic form of W in the prior, and therefore the posterior also is a normal distribution with mean, as it turns out, A transpose A plus B by A identity matrix inverse of that A transpose Y, and the covariance matrix of the posterior is small a times A transpose A plus Bi. Okay, so the posterior is a normal distribution, and one thing that we can do is we can say, okay, we'll set the value of W uh, to be the value of W that maximizes P of W given x of x comma y. So that maximizes the posterior distribution of W given the data. So that is called the maximum a posteriori estimate of W, and that for a Gaussian distribution or a normal distribution is the mean of the distribution. So that is this value. So we get W map is equal to the mean of the normal distribution of the posterior of the distribution of the posterior, which is a normal, which is this. Okay, so this, if we just notice, as compared to the MLE estimate, we have this factor extra. Okay, B by A times I. So yeah, I'm just wondering, because the thing is, this should go to the MLE estimate as we have more and more data. I'm just wondering why that should be the case here. I'm not quite sure, but this is the map estimate. And once we have this map estimate, then for a new x new, we can say y new is equal to, just hold on.